Good afternoon. So in my talk, I'm going to present some results from the development of this post-testing based leakage detection technology. I'd like to acknowledge our funding agency in ETL and also my co-authors at the Bureau of Economic Geology and Department of Petroleum Engineering at UT Austin. So here's the outline of my talk. HPT is actually not new. It has been used as a site characterization tool since 1970s, if not earlier. So the main motivation of our study is to assess the feasibility of using HPT as a leakage detection tool. So indeed, leakage detection is critical for ensuring that injected CO2 or other waste fluids safely stored in the geological repository during its performance period. So over the years, many technologies have been developed. So as we move toward more commercial scale applications, some important considerations to keep in mind, including the instrument's sensitivity, the application readiness, cost effectiveness, and the potential for optimizing monitoring network. In the last several years, our research group has mainly focused on the time domain analysis of pressure signals and their interpretation. So in this research, we switch to frequency domain. This is because, after all, the reservoir is pretty noisy down there. So compared to the traditional time domain-based analysis, the frequency domain analysis has two major advantages. First is it's less prone to noise interference, and the other main advantage is that it doesn't require extended period of shut-in. So, that's usually the last thing the reservoir operator would like to agree to. So for those of you who have experience negotiating with site owners, you probably know what I mean here. So in a nutshell, HPT stimulates reservoir volume at one or more different injection frequencies, and then acquire this impulse response relationships at those observation wells. So these relationships embed reservoir's physical characteristics in them. So when they quantify this so-called frequency response function, which is nothing but the ratio of the spectra of the observed signals to the injection signal. So then it has two equivalent attributes, the amplitude and the phase. So our main hypothesis here is that in a leak case, the frequency response function will show discernible deviation from that of the no leak case. So, so in the simplest application, this HPT can be used as a time-lapse leakage detection technique, and no reservoir model would be needed. Of course, we want to query the leak characteristics, such as the leak location. We still need a reservoir model. So before HPT can be applied to the field, we need to establish its theoretical basis and perform some validations. We start from this very classic leakage problem involving two aquifers and a single agritard. So in HPT test, the harmonic injection rate is superposed on top of baseline or nominal injection rate. So for our purpose, we shall assume that the baseline rate is deterministic. So the analytical solution to this problem has been well studied by many research groups. For infinite acting boundaries and constant injection rate, the Vichy derived a set of analytical solutions using inverse Laplace transform. So the solution was later extended to a multi-layer case by a group at Lawrence Livermore large spectral library, sorry. So here we see that HPT basically adds this beautiful oscillation on top of its constant ejection profiles. To derive some analytical results, our starting point is the same diffusivity equation, but with sinusoidal source term. And because we are mainly interested in frequency response, we obtain everything. We applied Fourier transform to obtain the solution in the frequency domain. So here it shows the leakage flux and the pressure response in the reservoir. So some important parameters to note here are the transmissivity ratio and diffusivity ratio between the upper and lower aquifers, and also this omega, which is the injection frequency. Is basically 2 pi over the pulsing period. So everything here is made non-dimensional. So given these analytical solutions, we can make many charts like this during the design of HPT test. So in general, we see that the amplitude attenuation increases with the increase of pulsing frequency. So at shorter pulsing periods, basically the source energy is attenuated very fast, and we don't see any significant deviation. But on the other extreme, at very long pulsing periods, we see basically some maximum deviation, some flat profiles here. So for practical purpose, if time is limited, the intermediate frequency ranges are going to be the most useful. Recall that the beta is the transmissivity ratio. So larger beta means the upper aquifer is less resistant to leakage flux, and so the amplitude attenuation becomes larger. For the same token, the uppercase omega here is the measure of wellbore resistivity to the leak. So larger resistivity means less flux on the wellbore, and thus we see also less attenuation. So then similarly, we can use this plot to for given reservoir properties, we can use this plot to figure out the detection range of HPT. So here it shows the sensitivity of the results to different observation locations and also the leak locations. So again, the key message here is that longer pulsing periods tend to reveal leaks farther away. So in this particular case, we see that pulsing periods, that's in a minute. So pulsing period greater than 1 day can reveal basically leaks like located 100 meters away. So we developed this 3D model, numerical model to validate the frequency domain solution. So to do that, we converted the pressure solution using fast Fourier transform, and the results show a relatively good match between the two sets of solutions. We have also done the multiphase flow simulation of CO2 injection into brown aquifers. So the trends are generally similar, although the required pulsing periods are much longer. We have reported some of those in GHGT 12 paper. So I'll use the remainder of the talk to present some preliminary results from the experiments. The main objective of this experiment is to validate the concept of HBT before we go to the field to demonstrate the technology. So the major equipment manufacturer for this experiment is this meter scale stainless steel tank that can hold 1 ton of sand and sustain up to more than 200 psi of pressure. So we use a wave generator to simulate different types of harmonic waves, square, sinusoidal, etc. And this tank is bundled with high resolution, high precision pressure transducers. And so we packed the sand carefully and inject water very slowly, using some very raw technology here. So for our leak test, we initially we simply let the leak flow into the air to sort of mimic the worst case scenario. So according to Darcy's law, basically we expect to see a linear response, a pressure response here, right? However, we obtain this very nonlinear behavior. So this, can be explained by the entrapped air in the sand. So we then injected some CO2 to expel the air from the tank and let it sit for several days before doing another experiment. And so that significantly improved the response. But we still see this, initial nonlinear regime around 40 psi. Basically, that's kind of sort of a turning point. Then we repeated several tests at different frequencies. So this 40 psi turning point persisted, but we were able to observe this pretty clear pressure fall off, the deviation from the non-leak case. So during all these tests, we release the tank pressure before, let it sit for several days before doing other tests. So what it turned out that that's not a good practice. So if we kept the tank in a pressurized state and only release it immediately before the test, we can get a pretty good linear response. So that's actually what we got, and we were able to fit a 3D model nicely to the pressure response. So in summary, for the experimental part, in the future we'll do more experiments and we'll keep the tank pressure in the pressurized state, and we'll also use the air tap water, and that's actually quite an important factor here. And so in conclusion, our simulation shows that HPD is a promising and very low cost, low technology technique. So in the future, we'll perform more lab experiments, and ultimately we'll go to the field to perform some field tests. Thank you.
We have a couple minutes for questions for our speaker. Can you repeat the question? So
yeah, the question is the sand wet pack or dry pack? So the sand is wet pack. We add water slowly and then pack it, and then in a gradual process. But still, we got some trapped air in it. So. Yeah.
I have a question, actually. Am I understanding correctly that to apply this to a field scenario, you would need to do some baseline to get a baseline response, and then you would compare later responses to that original baseline?
Yeah, that's as a time-lapse technology, a baseline is required.
So if for some reason there was an undetected pre-existing leakage zone in a reservoir, would the baseline data tell you that, or are you only depending on the comparison and on a leakage pathway developing with time? If there's a pre-existing leakage pathway, would you be able to tell?
Right. Yeah, that's a good question. So there are two possibilities. One is that of course it's hard to detect if the leak already exists. The other thing is that during injection, your pressure is higher than the original one. So maybe it still shows some pressure anomaly because of this increased pressure. Right. That's my hypothesis.
Great. All right. Any other questions?
how does the heterogeneity affect the application of your HPT?
Yeah,
How does heterogeneity affect it?
So basically, it's the same way as it affects all kind of pressure waves. So if there's a high permeability channel, we expect pressure will basically channel through those high permeability channels. So in that sense, the pressure observation location is actually pretty important. So, but that's a kind of a different subject.
All right, thank you again.